In this video, we'll see about how to simulate signals and system ideas in Matlab. So Matlab is a simulation tool with which we'll actually try to generate signals, try to process them, try to modify them, and then see what happens to them. So there are many softwares like Matlab. Like for example, there is an open source software called as Octave, and there is something called as Scilab, and even Python can be used for these simulations. But Matlab has some built-in commands, and the way the syntaxes are there for Matlab, it is easier and less time consuming for simulation of these exercises. So we will use Matlab for this course and simulate some of the ideas that we learn in signals and systems using Matlab. So in order to start with this, first you need to have the Matlab software installed, and to install that you can click here, and this will lead to a web page that will show you how to install Matlab, and you should sign up for it first with your email address, with your IIT Madras email address. And once you sign up and have an account, you can actually download Matlab, install it in your system, and then start working with it, start learning it. And to learn Matlab, so once again, the second link here, it will take you to this website where there are basic tutorials about fundamentals of Matlab, how to create a variable, how to add data to a variable, and how to manipulate a variable, and all those things will be there in this link. And if you want to see little more advanced level, so advanced levels such as working with little higher functions and some more complicated techniques of manipulating signals, then there is the third link which will show you the list of advanced functions and little bit intermediate functions in Matlab that are available for our signals and systems. So I would strongly recommend everyone to first install Matlab using the first link, and then go through the second link which gives you the basic tutorials of how to work with Matlab, what is the syntax, how to write a program, how to write a function, how to write a Matlab script. Everything is there in the second link. So I would ask every one of you to open the first and the second links and then go through the procedures and the information given in the first two links. And if you're further interested, please go through the third link also. So once you have installed Matlab, then the next step would be to now simulate, create some signals, and then see how it looks like, plot them, and then visualize, and then do some processing on top of them. So first we need to understand how to represent signals in Matlab. So the first thing that you have to remember is the signals and systems course talks mainly about continuous time signals. So if there is a continuous time signal, something like this, then let's say the signal exists between 0 and some a, this a can be equal to 1. How many samples or how many values of the signal, or let's say the signal is x of t and the x-axis is t, how many values of x of t actually exist between 0 and a if it is a continuous time signal? There are infinitely many values, right? So even if this a is really small, let's say even if it is 10 power minus 10, how many values exist between this 0 and 10 power minus 10? Once again, there are infinitely many values. So if I have to store this signal in a computer, how many points should I store? So how many points should I store like this? For a continuous time signal, it turns out that there will be infinitely many points, however small the signal is. Even if the signal is for 1 nanosecond, because it is a continuous time signal, there are infinitely many points between this beginning and the end of the signal, even if the duration of the signal is 1 nanosecond. So we cannot really store continuous time signals as such. The only way that we can store and simulate them in a software digitally is by discretizing them. What do we mean by discretizing? We say that, okay, there can be infinitely many samples, but what are we going to do? We are going to only take a finite number of samples. And how are we going to take this finite number of samples? We are going to discretize the time axis. What do we mean by discretizing the time axis? So if my time axis is between, let's say, 0 and some a, now what I'm going to say is, I'm going to say that I will take one sample between 0 and some capital T, another sample between t and 2t, another sample between 2t and 3t, and so on. So basically we are breaking down the time axis into grids. So this is one grid, this is the second grid, and so on. So this breaking down of the time axis into smaller grids is what we refer to as discretizing. And then in that grid, now let's say we've broken that into grids like this, and your function is something looking like this. In the grid, we approximate the amplitude of the function to only one point. So in essence, what we are trying to do is we are going to approximate a continuous time signal with rectangles at each and every point. So this is exactly what we get if we do that. A continuous valued signal, you discretize the time, which means you grid the time axis, you create multiple grids on the time axis at regular intervals with uniform size. Then what you do essentially is convert this continuous time signal into multiple sequence of rectangles, each rectangle carrying different amplitudes, and that amplitude corresponding to the continuous time signals level at a particular grid. So this is discretizing. So once we discretize, then what we can do is we can represent or store this signal just by storing the value of the amplitude of the rectangle in a given bin. So how many bins are here? So now we have, let's say this is 10, and now let us say we have 1, 2, 3, 4 up to, let's say we have 10 bins now. So we have 10 time bins, okay, and the corresponding value can be something like 0.1, 0.2, 0.25, so on. So for every bin there is a corresponding amplitude. So once you discretize, what effectively we will have is an array of time indices and the corresponding amplitude values. Now I mentioned earlier that the way that we are going to construct these grids is that the time axis is going to be broken down into uniform grid sizes. And what should be the size of this grid? That is the width of this grid, and this is what we'll call as the sampling time. Okay, so we'll choose a sampling time. It means that you're going to sample the continuous time signal at that time instant and then move from the time instant to the next time instant, which is Ts away, and then sample it again. So you keep sampling the continuous time signal every Ts seconds. So that is what we refer to as the sampling time. And when do you start sampling? You start sampling at some particular time, what we call as the start time. And then you stop sampling it at a particular time, what is called as the end time. So what we don't specify, if we don't specify the start time and end time, what will happen? Then it might so happen that the signal might exist from t equals minus infinity to plus infinity. If the signal exists from minus infinity to plus infinity, even if you discretize, then there could be infinitely many samples, then we cannot store. So we need to have only finite number of samples, only then we can store. To make sure that we have only finite number of samples, we should have a finite start time and a finite end time. So I'll say that my signal starts at minus 2 seconds and ends at 10 seconds. And then I'll sample at every 1 second. In that case, I'll have 12 samples. Okay. So this is how we are going to discretize any continuous time signal so that we can represent that. So now here we have an example. So there is a continuous time signal which is like a sinusoid, and it exists from 0 to 1 second. And if we discretize that with a sampling time of 0.1 seconds, then we have 10 samples, like 0, 0.1, 0.2. At every Ts instance, we'll have one sample, and it looks like this. Now, if we discretize that with 0.15 seconds, now we have fewer samples. As you can see, as you increase the sampling time, what happens? You would sample the signal less often. And because you are sampling the signal less often, you will get lesser number of samples. So clearly, when you have Ts to be large, the visualization of the signal using these samples doesn't look great, right? So in order to visualize the signal better, in simulations, what we do is we try to keep Ts as small as possible. We can have Ts to be equal to, let's say, 10 power minus 6. So 1 microsecond. So if we have 1 microsecond, then how many samples we'll have between 0 and 1 for the sinusoid? We'll have 1 million samples. So the number of samples that we need to process also shoots up. So there is a fine trade-off between how many samples you should pick, that is what should be your Ts, how small it should be. So if you choose it to be very, very small, then you'll have large number of samples to process and it will be very slow with your computer. So we should try to keep Ts slightly larger, but if you keep it very large, then what will happen when you visualize it, when you plot it and visualize it, it will not appear very nice. For example, the third plot here, it does not really look like a proper sinusoid because we have very few samples. So there is a nice trade-off between this visualization sampling time versus the sampling time that is appropriate for computation. So this is something that we have to pick and choose. Typically, we say that 1 millisecond is okay. Actually, there is an optimal value of sampling time that is given by something called as Nyquist sampling theorem. We'll talk about it in the signals and systems course, but there is something like this which you can connect to it later. Okay. So, in order to describe or represent any signal, now we need the time and the corresponding amplitude value. So, we will have two arrays, what we call as the time array and the signal amplitude array. So, the time array is going to contain the time instances at which we are sampling the signal, and the corresponding signal's value will be inside the signal amplitudes array. Okay. So, for example, if I have a signal which is existing between -1 seconds to 3 seconds and I am sampling every 1 second, then the time array will contain -1, 0, 1, 2, 3, and this x of t is simply containing the corresponding amplitudes of the signal and those time instances. Alright, now let us see some simulation exercise. So, this code here is going to plot a sinusoid. So, as you can see here, we have a cosine signal between -1 to 1 second. So, the left hand side topmost is the representation of the signal with a sampling time of 0.05 seconds, and the left hand side bottom signal is the same signal but with a sampling time of 0.1 seconds. So, as you can see here, we have more samples when we have sampling time to be small and lesser samples when our sampling time is large. So, what is important when we visualize this signal is that we have to use both the time array and the signal array. What if we ignore the time array and then use only the signal array? Then things will be not correct. Why? Because the right hand side plots are plotting only the signal array. It's not plotting or taking into account the time array while plotting. What is it doing? It is just having an array of signal amplitudes and it is just plotting with respect to the index. So, in the first one there are 41 samples, in the second one there are 21 samples. So, the first one here, the rightmost top, it simply says that okay, I have this as the first sample, this as the second sample, this as the third sample, and so on, and it is just plotting with respect to the array index. The x-axis here is the array index, not the time. So, you have one representation. Similarly, below here we have the x-axis to be the array index. There are only 21 points, and then you plot the same signal. Now, the signal looks weird, right? This is not what we generated, and hence it is important to have both the time array and the signal array. Only when you have both, you can visualize this properly. So, when you want to visualize this, you have to ensure that the x-axis here in both the cases are given by this corresponding time array. So, you have to plot the values on the x-axis from the time array and the y-axis from the signal array. Then you can visualize the signal. If you simply plot the signal with the signal array and the x-axis is the index, then you will not get a proper visualization. As you change the sampling time, you will get different patterns which do not correspond to the actual signal. Hence, a signal is always represented by two arrays. One is the time array and another one is the signal array, which contains the amplitude corresponding to the time instances present in the time array. Now, how do we plot all these things? So, we can use the plot function in Matlab to plot all these things. So, as you can see here, I have used the plot function. So, you can just use plot of time array comma signal array, which basically is nothing but plot of x-axis values comma y-axis values, and you will get this plot. Alright. For more details about how the plot works and what are these functions, please go through the tutorial that I mentioned in the beginning of the video. The second link contains a lot of information about all these functions and so on. Alright. So, if we want to change the time here, all we have to do is change the start time and end time in our code. So, here the start time is -1 and the end time is +1. So if we want to start at, let's say, -2 and end at 0, all we have to do is change this to -2 and the end time also to 0. Now if you plot this, we'll have a signal which is starting at -2 and ending at 0. As you can see here, the signal started at -2 and ended at 0. So we can also change the sampling time. So let's say if we change the sampling time to 0.01 seconds. Now what happens? So as you can see here, now we have a lot of samples here. Okay, and clearly we have more samples and the visualization now looks even smoother. So that's the advantage of having more number of samples. All right. So what if we want to add or multiply or subtract two signals? Then what do we do? So there are some things that we have to keep in mind when we do this. It should be necessary that when you add or multiply two signals, they need to be time aligned. What do you mean by time aligned? Now let's say I have two signals. One is x of t, another one is y of t. But let's say y of t is starting at some other point, not necessarily at 0. X of t is starting at 0, but y of t is, let's say, starting at 15 seconds and then ending at 25 seconds, whereas my x of t is starting at 0 seconds and ending at 10 seconds. Now if we take samples, let us say our sampling time is 1 second. So we'll get 10 samples from here because it is between 0 and 10. Now here it is between 15 and 25. Even here we'll get 10 samples. But the time array here will be different. The length of the signal array will be the same in both the cases. So just because they are the same, you cannot simply add element wise in this case because they are not time aligned, because the time array will be different. Here the time array will be 0, 1, 2, 3, so on, whereas here it will be 15, 16, 17, so on. So the time array here will contain different points. So they are not time aligned. So what we should ensure when you multiply or add or subtract signals is that they are time aligned. What should we do for that? First thing is they should have the same sampling time. If they don't have the same sampling time, we will not be adding the signal properly. So in one case we might have 2 samples in 1 second, whereas the other we might have 10 samples in 1 second. So we cannot add them properly. So they should have the same sampling time and they should have the same start time and end time. If these conditions are satisfied, then we can say that okay, they are all time aligned. Basically what it means that in the Matlab representation or the digital representation, the time array of the signals that we want to add or subtract or multiply should be the same. Okay, and when we want to multiply two signals in Matlab, the syntax is dot asterisk, not simply asterisk. Okay, so let's say we are going to use dot asterisk. Let's see what happens when we multiply two signals. So now we have two signals. So the blue one is a cosine signal and the red one is a sinusoid, a sine signal, and they are all exactly starting at -1 and ending at +1. So the start time is the same as end time and the sampling instance is also the same. The sampling time is also the same. So we can multiply and then it is properly time aligned. So this is what we should get and this is what we are getting properly. Now let us say this is not time aligned. Then what happens? Let's see what happens when it is not time aligned. So in this case, we have a signal where we have two different sampling times, but the length of the signal array is the same. What do we mean by that? So here, the first blue one is created with a sampling time which is equal to 0.05 seconds. And the red one now is created with a sampling time which is equal to 0.075 seconds. So we have two signals, both are containing the same number of samples. That is, here we have 41 samples. Both of this blue and red contain 41 samples, but the blue one is actually from -1 to +1 with a sampling time of 0.05 seconds. And the red one is actually from -1.5 seconds to +1.5 seconds with a sampling time of 0.075 seconds. So they are completely time misaligned. They have different sampling times, but the number of samples are the same, which means the signal array will contain equal number of samples, and if you simply add the signal arrays without even taking into account the time array, you will get some garbage like what we have in the third plot here, which is not what we want, right? So this is not what is supposed to be getting. Clearly, we should align them before adding or multiplying. So now what if the sampling time is right, but the start and end times are incorrect? Once again, see for example here, the blue one and the red one, their sampling times are the same, but the start and end times are different. And if you add them once again, you will get an incorrect signal. So this is also an incorrect signal because it is clearly not aligned at the beginning and at the end. So one thing that we can do is, if two signals have the same sampling time but different start time and end time, then what we can do is we can pad zeros in the beginning and end. So what do we mean by that is, let us say we have a signal here which is 0 to 10. So x of t is between 0 to 10, but my y of t is between 15 to 25. So what I can do is I can assume that from 10 to 25, x of t is going to contain only zeros, and I can assume y of t is going to contain only zeros from 0 to 15. If I do this, then essentially what I have done is padding zeros here for x of t and padding zeros here for y of t. Now they are going to start and end at the same time. The starting time is going to be 0 and ending time is going to be 25. Now we have fixed the starting and ending time by padding zeros, and by padding zeros, now everything has been aligned. So once you align and you see what is the sum or product, that will now be exactly what we want. So as you can see here, the blue one was out of time, did not exactly match the timings of the red one. So what we did, we added zeros for the blue one in the beginning and for the red one at the end. Now we can add them sample by sample and it should be fine. So this is how you add or subtract or multiply signals. So now you can take this code, try to multiply with it, try to subtract y of t from x of t, and then see what happens. Try and see why it is important to time align signals. So essentially what we mean is the time array of the signals that you are going to work with should exactly be the same for all the signals that you have in your signal processing code. So if the time arrays are different, then you cannot process them. So ensure that they are all the same. Okay. Now, what if the signal that we are working with is a complex signal? So it is easy to visualize a real signal. You have just in the x-axis time, in the y-axis the amplitude. What if it is a complex signal? How can you plot the amplitude in just the y-axis in the complex signal? So of course we cannot. So there are different ways of visualizing a complex signal. Either we can visualize it like a 3D plot, or we can separately plot the real part and the imaginary part, or we can plot the magnitude and the phase. Now let's take an example and see how it looks like. Now let's say this is our signal e power t plus j2 pi t. This is a complex signal. So let's see how it looks like. So a 3D plot is this, where we have the three-dimensional representation. The blue curve here shows the samples and the three-dimensional representation of the signal in 3D. So the time axis is here from -1 to 1, and we have the real and imaginary parts which are visualized in 3D. So as you can see here, this has a specific real part, and that real part is on the axis and it coincides when you rotate the graph, and similarly there is an imaginary part and real part, and once again when you rotate the graph it coincides with the real part. So you can rotate the graph and then see how it looks like at different angles. Now the other representations are simply plotting the real part, imaginary part, and the magnitude and the phase. So here in the blue one shows the real part of the signal, which we saw actually as projecting in one of the planes in 3D. So basically if you project onto the real plane you get this, and you project onto the imaginary plane, so that is the time and imaginary plane, and you get the red curve, and if you plot in the time real plane you get the blue curve. So this is the same signal that we had taken as the example. We saw the 3D plot. Now instead of seeing in 3 dimensions, we are projecting into one of the planes and then seeing it. That is the real and imaginary. Another way of visualizing that is the magnitude and phase. So the magenta one here, the left bottom, shows the magnitude of the same signal, and the black one here is showing the phase. The phase has a weird pattern here, that is simply because when we find the phase is always between minus pi to plus pi. So because of this reason, when you compute a phase which goes beyond minus pi to plus pi or 0 to 2 pi, it wraps around. So a phase of 3 pi would actually in the plot give you only pi, because it wraps around and it has to be between minus pi to pi or between 0 to 2 pi. In Matlab, it is always between minus pi to pi. So if you have a phase of, let's say, 3 pi by 2, it becomes pi by 2 and so on. Now, how do we compute energy and power of a signal? So remember, how do we compute energy? So we just compute the area under the curve x of t squared dt in some interval a to b, right? So this is how we compute the energy. But here we cannot use integral because we are already discretizing the signal, which means we are breaking that down into multiple rectangles, multiple grids. So how do we compute area? So we know that to compute area, we can actually use this approximation where we have broken down into multiple rectangles, and you can just find the area of each rectangle and then add them up. So if you want to find the area of each rectangle, how do you find the area of the rectangle? The length into breadth. The breadth is ts and the length is whatever is the value of the signal at that particular point. So essentially what happens now, so if you want to integrate between a to b x of t dt, the value of the signal at x of t is given by x of a plus nts, where ts is the width of the rectangle and a of nts tells you which is the time instance. For example, now in this case, let us say our a is 0, which means our starting point is 0 and ts is 1. Then the first sample is at 0 plus n is 0, 0 times cs. So the first sample is at x of 0. Okay. So the time array will now contain 0 first, and the signal array will contain the corresponding value x of 0. Now the second one is substitute n is equal to 1, that is a plus ts. So a plus ts is 1. Now the signal array will contain the value x of 1. Now substitute for the next sample a plus 2ts. This is 2. This will contain x of 2. So the area under this signal is now actually going to be nothing but sum of area of these rectangles. And what is the area of the first rectangle? The area of the first rectangle is ts times x of 0. The area of the second rectangle is ts times x of 1, and so on. So when you compute the energy, what do we need to do now? The length changes when we compute the energy, because we are computing the energy by squaring the signal. So the square of the signal is the length at every point. So the energy now is computed like this, so on. So basically what we are doing is taking a continuous time signal, discretizing it, representing that using a sequence of rectangles. You find the area of the rectangle and then add them together. That gives the energy of the signal. And remember, power of a finite duration signal is always 0, and we cannot represent an infinite duration signal in simulations. Alright. So the energy is always finite. So let's see an example. So we have a sinusoid here at two different sampling instances. One is at sampling given by 0.05 seconds, another one is at 0.1 second. Even though the sampling times are different, the start and end times are the same. So if you change the start time and end time, of course the length of the signal changes, so the energy will change. Now here we have fixed the length to be the same, but sampling times are different, but we are getting the energy to be roughly the same. There is a 0.05 difference. The 0.05 difference comes mainly because, so we are starting the so it is because of the length of the rectangle. So when ts is equal to 0.5, the last rectangle here is of width 0.5. When the TS is equal to 0.1, the last rectangle here is of length 0.1. So the length of the rectangle changes as you change your sampling time. So because of this, what happens? The length of the last rectangle will always be different when you change the sampling time. So when you compute the area is computed between the interval a to a plus nts. So as you can see here, what happens is that the last rectangle for sampling time of 0.5 seconds is between 1 and 1.05 seconds, whereas for a sampling time of 0.1 seconds, the last rectangle is between 1 and 1.1 seconds. So there is a difference. The length of the signal itself changes when you compute the area for different sampling times, and this introduces a small error in energy computation. So there is always a small error in the energy computation, and this can be minimized by choosing a very, very small sampling time. So this is bound to happen when you change the sampling time. So there is nothing wrong in your computation. Only thing is we can minimize this by changing the sampling time to be as small as possible, whichever is easy for our computation. Now we'll have multiple exercises. In fact, we'll have 5 Matlab exercises. So these are in some sense like laboratory exercises for simulation of concepts that we'll see in signals and systems. The questions will be uploaded in this link, thegrader.mathworks.com. For this course, you can get the link here. So the page, when you click on it, will look like this. The first simulation exercise is already up. So when you click on the first simulation exercise, it will show a list of questions. So in this case, there are 2 questions, time shifting, time scaling. There will be some more questions added. And when you click on time shifting, it shows the question here. So basically the question here is you have to create a function which will take an input. Remember, the signal is always represented by a time array and a signal amplitude array. So here the input is time array and signal amplitude array. Together it represents a signal. So input is a signal and the amount of time by which you have to shift it. So this is a Matlab function that you have to write, whose input is already fixed. You have to do some processing and then write a code for computing the output signal. The output signal once again is represented by the time array and the signal array. So this is the place where you have to enter the code. So you can write the code, simulate and check if it is working properly in your laptop, and then finally the correct code alone you paste it here. A sample you can run here. When you say run function here, it will run whatever you have coded for that particular sample alone. Alright, and once that is done, you can just verify for that particular input how it works. And once that is done, finally what you can see is there is a way to check if your code is correct or not. So you can click on submit, and the moment you submit, immediately it will be evaluated. There will be multiple checks for that exercise. So if it is correct, then all the checks will be verified and then you will get a green signal. If some of them are wrong, then you'll get a red signal. So you have to ensure that everything is correct in order to get full marks for this exercise.